seemingly very, very similar, right? Every node, every edge. Now, the Eulerian cycle problem is incredibly important in the history of mathematics because take a stroll in the city, and somebody said, wouldn't it be nice if we can start from one point, exactly back to where we started. And they kept trying, and they always ended up in a different place. So finally they said, why don't we ask the famous mathematician Leonhard Euler, and Euler was then actually sponsored by the Tsarina, by Katerina the Great, and Euler did that what the mathematicians do, abstracted. So this is, he says, well, every piece of land can be collapsed into one point, and the edges are the bridges. So we get this graph, and the question is, does this graph have an Eulerian cycle? Hamiltonian cycle come actually from a little puzzle. So again, this was a very specific graph, and the question was, the puzzle was to find what we call today Hamiltonian cycle in this particular graph. It does have Hamiltonian cycle, but you can see it's a bit tricky to find it. So if I give you the graph, even in such a small graph, it's actually quite tricky to find the Hamiltonian cycle. Now, what is computational complexity? Formally, we're saying how many Turing machine operations would it take to solve a problem of size n, and what is the size for a graph? We can say maybe the number of nodes plus the number of edges. That's good enough to measure the size of a graph. And we really don't care much about it. You can say Turing machine, but the answer would be take any machine. Take the MacBook, take the instruction set. How many machine operations would it take to solve it? And we typically are interested in just knowing how fast does it grow as a function of n, and we like to look at problem where it doesn't grow too fast, and it means it grows polynomially as n to the c, so for some fixed c in the size of the problem. And many problems are in polynomial time, is a given number even. Just read the number, look at the final digit, so linear time. Is a given number square? Is it in polynomial time? Now, to answer that question, you have to be old enough, because if you're old enough, you're taught to do longhand, square root by longhand in high school, and if you go back to that algorithm, you'll see that this actually was a linear time algorithm. What about Eulerian cycle? So Euler proved a lemma which is actually not too difficult, that the graph of Eulerian cycle, if and only if every node has an even degree, because the cycle will have to enter a node and exit a node and use different edges. Therefore, the degree must be even of every node. And now we can see that this graph, in fact, no node has even degree. And therefore, the answer to the citizen of Königsburg, no, you cannot take the work that you want to do. It's impossible. And what about Hamiltonian cycle? Can we find it efficiently? Well, one thing we can easily do is try all cycles, but that's a huge number. There are about n factorial such cycles, so this is a very large number. We can try to be smarter and use something called dynamic programming, in which we create Hamiltonian paths and we kind of piece them together and we get longer and longer paths. And then you can do it in times 2 to the n. Now, just to understand how big is 2 to the n, if I take a graph with 200 nodes, the number 2 to the 200, imagine you have a machine that is very fast. It can run, every machine cycle takes one Planck time constant, which according to quantum mechanics is the smallest possible time unit. I think it's 10 to the minus 44 seconds or something like that. And you started it just on the Big Bang. You still have not finished solving the problem, okay? Not enough time has passed since the Big Bang. And so the big question is, can we do better? Can we do it in polynomial time? That is the questions about, and in fact, there are many, this is just a sample problem. There are many problems which we only know how to solve exhaustively by trying all possibilities, but we don't know how to solve in polynomial time. Now, there is a key observation that was made in the early 70s, which is really a very intuitive observation. If I give you a candidate solution, it's easy to check whether or not it is Hamiltonian cycle. I give you a cycle, and you have to check that you visit every node exactly once, and between every node there is an edge. Every pair of node, neighboring node, there is an edge. So checking is easy. And this seems to be the case There are many, many such problems, and therefore we give it a name for such problem. We call them NP, for the problem that can be checked efficiently. And you can think of many other examples. Think of factoring number. Seems to be a difficult problem, but if I give a factorization, checking is easy. Just multiply the number, see whether you get back the original number. And this is a well-known phenomenon that in many, many cases we know how to check, but we don't know how to solve the problem. So P versus NP is almost a philosophical question. Is it the case that checking is really easier than discovering solutions? So this is what it means. Now, our intuition says, well, surely checking must be easier, because think about even the language, our language assumes it. So there is a metaphor, finding a needle in a haystack. That seems to be a difficult problem. But if I tell you the needle is here, nobody thinks it's a difficult problem to verify the needle is there. Just put your finger, you see a little blood, yes, the needle is there. Okay? Checking that the Sudoku, if you know Sudoku is this Japanese puzzle, solving may be difficult, some Sudokus are difficult, but checking is trivial. And you know, we all think that reading a proof, even if it's a difficult proof, should be much easier than coming up with a proof, which we think requires creativity. So our intuition tells us that P must be different than P. Checking is easier than discovering, but we don't know how to prove it. Now, we can imagine a world in which P is different than NP. What's the consequence of this? Consequences are that many problems have no efficient solutions. But it may mean that RSA encryption is probably safe, because RSA encryption depends on hardness of problem. We assume that certain problems are hard. So it's kind of bittersweet news, right? We have problems are hard, but we can use the hardness, for example, for encryption. Why is it so important to prove that P is different than NP? When I was, years ago, I was at IBM research lab in San Jose, and the director of the lab was a physicist. And one day, I get a messenger from the director of the lab. The director wants to understand about this P versus NP. I said, okay, what is the question? He said, it is commonly believed that P is different than NP, right? I said, yes. He said, the director wants to know, why don't you guys just accept it and move on? Which is what physicists do, right? They said, there's no evidence that this is, take it as a hypothesis, there's no evidence for the contrary, just accept it and move on. So I said, well, if we don't understand it, first of all, if you cannot prove it, means we don't fully understand it. And also, we can always imagine that there is some bad guy, choose your favorite bad guy, who did prove that P equal NP, and therefore cracked RSA in reading all our encrypted messages. Okay. So that's why we really feel that we need to prove it. Now, is it possible that P equal NP? So Scott Aronson, I'm quoting him, and he will talk about it tomorrow. And he wrote very beautifully, he said, if P equal NP, then the world would be a profoundly different place than we usually assume it to be. There will be no special value in creative leaps, no fundamental gap between solving a problem and recognizing a solution once it is found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. And so you can see that his belief is that P must be different than NP. Now, suppose that P is equal to NP. So the good news is that we can solve efficiently many, many problems, but we have lost RSA encryption because we can now break RSA encryption because we can to factor numbers, we're going to just guess the two factors and factor the numbers. Now, is it possible that P equal NP? Absolutely. All it will require is discovery, very clever algorithms. And actually, we are very good at coming up with clever algorithms. You have to remember, linear programming, it took 40 years before people found people found a polynomial time algorithm for linear programming. It took a long time, but people came up with a very clever algorithm based on interior methods. Now, a beautiful theory emerged in the early 70s, and that's the theory of NP completeness. So NP complete problems are, in formal sense, the hardest problem in NP. Hamiltonian cycle is NP complete, is the hardest problem in NP. That means NP equal NP if and only if Hamiltonian cycle is in polynomial time. And therefore, it's a very inviting target. There is a website that you can go to, and it contains proofs that P equal NP, and proofs that P different than NP. And to prove that P equal NP, Hamiltonian cycle is a favorite target for people. I have a polynomial algorithm for Hamiltonian cycle. Many, many false proofs have been published for Hamiltonian cycle in particular because it's a nice, elegant problem. There are thousands of problems that are NP complete. It's enough for one of them, it's enough to prove that either it's in polynomial time or not, and we have resolved this open question of P versus NP. And just kind of a brief, 50,000 feet history of the problem. So the problem that are things that require exhaustive search and nothing else. People have thought about it already in the 19th century, but really formally research started in the early 50s in the Soviet Union, the Peribel project, that for 20 years made lots of papers, but really no significant result, until in 71, Steve Cook proved the Boolean satisfiability, which I'll define in a minute, is NP complete. Then Karp came up with 20 other NP complete problems. Leonid Levin, independently in the Soviet Union, came up with a paper that did both Cook and Karp in a very short paper. And then there was a famous book, Garin Johnson, 1979, that kind of popularized the theory, and many red people learned the theory from this one. And then, as we said, 2000, Clay Institute put an award of $1 million. Now, let's go back to Boolean logic. So in 1847, George Boole publishes a book, and the book contains, it's the first book in mathematical logic, in a sense, until then, logic is a branch of philosophy. And Boole came up with the first mathematical treatment of logic, and in particular with an algebraic treatment of logic. So Boole's insight was that logical conjunction, the AND operation, can be viewed as multiplication, and the OR operation can be viewed as addition. And now we can talk about various laws. It's commutative, it's associative, it's distributive. You can come with various laws, and you end up getting Boolean algebra. So this is really the beginning of mathematical logic. This is a picture I showed also yesterday. This I'm visiting in 2017. I visited Ireland College, Cork, University College at Cork, and they let me in the library hold Boole's personal copy of his own book. My hands were shaking. Amazing. So what is Boolean satisfiability? And this is the modern formulation. So you imagine you have an expression using Boolean variables. So these are variables can only get the values 0 or 1, false or true. And the operations are the AND operation, and the OR operation, and the NOT operation. And the question is, can you find an assignment to the values such the whole expression would evaluate to 1? That's what we call to satisfy the expression. You want to put something so the whole expression value to true. 1 is true and 0 is false. And this one, it's easy to see that there are only 16 possibilities, so very quickly you can check them out, and you see that if I assign x1 and x2 0 and x3 and x4 1, it will become true. But this method only works for 4. Imagine even if it's 40, it's going to be too large. And in reality, we want to solve problems with thousands, hundreds of thousands, even millions of variables, and I'll come back to that in a few minutes. So we need a method to solve this problem. And people already realized that we need such method starting in the 19th century. So William Stanley Jevons, who was a follower of Boole, actually built a machine called Logic Machine that can do this reasoning about 4 propositions, okay? But still, he said, I've given much attention, therefore, to lessening the manual and the mental labor of the process of logical reasoning. And Ernest Schroeder, a German algebraist, wrote kind of an amazing quote, getting handle on the consequences of any premises, or at least the fastest method for obtaining these consequences seems to me to be one of the noblest, if not the ultimate goal of mathematics in logic, right? So if you're doing mathematics or logic, this is the ultimate goal, okay? Find a fast method to solve this problem, which by now we are questioning whether it's possible to find a fast method because, as we know now, Boolean satisfiability is NP complete. And if the conventional wisdom is right that these problems are hard, then we cannot solve these problems. But even though complexity theory may suggest that these problems are hard, starting from the mid-50s, people start to actually write software to solve this problem because it's a central problem. So in 55, there was the first paper that built a program called Logic Theories that did Boolean reasoning. And then amazingly, in 1958, the National Security Agency, so this is the agency in the United States that does what we call signal intelligence. In fact, they're probably listening to this talk right now, and therefore I'm going to give them credit. And they already funded research on computational methods in the propositional calculus to be run by Davis, who was a logician, and Putnam, who was actually a philosopher. And David Putnam published another paper. This paper, by now, it's declassified, so you can actually find that paper. That paper basically recommended the resolution for propositional logic. And then there was another paper in 1960, and a third one in 1962. And these papers together gave rise to what we have been calling DPLL for Davis, Putnam, Logeman, and Loveland. And this became the basic algorithm that has been running, people still use it today. And the idea is you convert the formula to what we call conjunctive normal form. This is the formula in conjunctive normal form. It's a conjunction of disjunctions, and negations are always applied to variables. Even though in principle, you can mix all the operations. Here it's done in a very particular syntax, and we know you can always convert it to this normal form, and it makes things much easier. And then you run a backtracking search. And what does it mean, a backtracking search? You assign a value, and you propagate it as much as possible. Then you choose another value, and you keep doing it. And either you solve the problem, and if not, you undo some of your decision, and you try some other decision. So this is called backtracking. You go back, and you say, well, it was a mistake to assign x1 to be 1. Let's assign it 0, and let's see what happens. You basically, this is the form of exhaustive search. With some heuristic, which we call unit clause preference, and what is this heuristic? The heuristic says, imagine that one of the disjunctions is the general disjunction, contains a single variable, positive or negative. Just imagine, it just said not x1, because I assign x2 and x3, let's say, to be 0. Then you know that if the disjunction says, if this disjunction is degenerate, and it's true, it means that x1 must be false now. So if you see that one of the disjunction is a unit clause, we call it, then to say, okay, now there's no more choice about this variable, pursue it. So this is a basic heuristic. And this method has been, people have been playing with it starting from the early 60s for the next 30 years, making very, very slow progress, solving problems maybe with hundreds of variables by the early 90s. And then some magical event happened in the mid-60s. And the magical event was the discovery of heuristic. What are heuristic? Heuristic are algorithmic techniques that are empirically effective, but we cannot actually prove that they're effective. It's just empirically. And these are 5 key heuristics, and the method today is called CDCL, for conflict-driven closed learning. I'll explain it in a minute. It's one of the heuristics. And each heuristic for SAT is a good heuristic for life. So pay attention now. Okay. One is backjumping. What is backjumping? Backtracking, you realize you make a bad assignment, you undo it. And you go one level up. There is a search tree, and you go one level up the search tree. Backjumping means, no, if the assignment is bad, do some analysis to realize maybe the mistake was made higher up. So jump up as much as you can. So what's the moral of life? When you make mistakes, think deeply about and really learn from your mistakes. Smart unit clause preference. So smart unit clause preference. So in 2000, the SHAF, it was a team at Princeton, they decided to do something that it's not clear why people did not do it before, to profile the code. Profiling means that you gather statistics where the program spent its time executing, which instructions are being executed. And they discovered that 80% of the time was doing unit clause preference. Remember, unit clause preference was just doing this obvious, very simple heuristic. So why was it taking so much time? Well, in order to identify unit clauses, you have to keep a count next to every clause, every disjunction, to say how many variables does it have. And every time you assign a variable, you have to update the counter. Every time you unassign a variable, you have to update the counters. So you spend a lot of time updating counters. And so they come up with a very nice data structure that meant that you have to update counters when you assign variable, but you don't have to worry about unassigning variable. So you saved a lot of time dealing just with counters. Conflict-driven closed learning. So Again, the idea is learn from your mistakes. If an assignment is bad, do an analysis, what's bad about this assignment, and write a new clause that will block you making the same mistake again. So that, again, this is learn from your mistakes. Smart choice heuristics. So I call it Brainiac versus the speed demon. So the people in this audience are typically Brainiac. And they think that being smart is the most important things in the world. But it turns out, what is the issue here? You have to choose the next variable to assign. How to make the good choice. You want to choose the good guy. So people develop all kind of heuristic of making a good choice, and the goal would be to minimize the size of the search tree. Turns out that if you spend too much time choosing, the search tree is smaller, but you spend a lot of time making choices in life. I have a postdoc. We go out to group dinners once a semester. Everybody is done eating, and he's still trying to choose the best dish to eat today. Okay? And we keep telling him, it doesn't matter. Just choose. Just choose. So this is Brainiac versus speed demon, and the terms come from the story, the comic book story of Superman. Superman has some enemies. Brainiac is one of his enemies, and Brainiac is smarter than Superman, and speed demon is faster than Superman, and Superman always wins because he's just the right compromise between being fast and being smart. And finally, restart. So you go up and down the search tree. At some point you say, this is not working. Let's just drop this and start from the very beginning. And why it is useful? Because in the meantime, you have made many mistakes. And each time you have made a mistake, you learn a new clause. And you added a new clause, which means you're not going to repeat the same mistake. So at some point you say, you know what, I'm going to start a whole fresh search, but now I've learned from my mistake. So when I do it again, it will be a better search. And together, these heuristics gave us today such solver that can solve problems using millions of variables. Just amazing progress. This plot was put together a few years ago by Sanjit Shesha from Berkeley, and he showed what happens if you take one benchmark and you run 12 years of such solver on the same benchmark. And he showed that one instance of one such problem that took 800 seconds in 2000 was solved in 1 second by 2012. So the dramatic progress over a decade, and this progress is still continuing by social process we do not fully understand. People are coming up with clever ideas all the time. And in fact, this become the progress has been so impressive that about 2 years ago, Don Knuth received a major award from SAM, it's a Society for Industrial and Applied Mathematics, and he was asked to give a big lecture, and he dedicated the lecture to satisfiability. Turned out that, Don Knuth is the closest we have to a patron saint, a live patron saint of computing, and he's been working since the 60s on the art of computing programming, and he was going to publish volume 4, but volume 4 kept growing, so it's coming out in sub-volume, which he called Fascicle, and Fascicle 6 you can buy today is all about Boolean satisfiability, which Knuth called it the story of satisfiability is the tale of a triumph of software engineering. I would have called it algorithmic engineering, blended with rich doses of beautiful mathematics. And the progress has been so impressive that now SAT is not just an academic research activity, it's an industrial practice. Today, Microsoft Research has been the forefront of using SAT for industrial software development. As we speak now, there are hundreds of servers in Microsoft running and solving Boolean satisfiability for all kinds of tasks. I can spend a lot of time describing these different things, but these are all aspects of software engineering that this is now being used by Microsoft. And I want to use it now. This is kind of a segue for the second half of my talk. Really, the first half in some was an introduction. I want to talk to you about a specific application that we have pursued at RISE that have to do with this kind of software engineering type of application for using satisfiability. So, and the goal is to what we call functional verification of hardware and software system. So, as you can imagine today, building a hardware and software system, your industrial activity, a huge economic value, estimated about $750 billion per year. And anybody who's written a program knows it's really hard to write a program that does exactly what you wanted it to do. You had something in mind, it's all clear in your head, you write it down, you got all the typos out, all the semicolons are in the right place, and you run it, and it doesn't quite do it, and you discover there are bugs. We just heard before about how hard it is to get bugs out of software, out of proofs. And so it turns out that when you look at the cost of the building computing systems, functional verification takes more than 50% of the cost. Some estimates are as high as 80%. That is, you write the code, but since we introduced, what was it, a bug and a half per line, we spend most of the time in getting the bugs out. It's more expensive to get the bugs out than to write the code in the first place. And if you are in around, we heard even before, around, we have a whole area of research called formal methods, where the goal is, the golden standard is to do what we call formal verification. In formal verification, we want to build a mathematical model of the system under verification, and correctness become a mathematical theorem, and we want to prove the theorem, and if we succeed, then we say, oh, now we are very, very certain that this is correct. And as we heard in the previous talk now, this is something that happens more and more in industry, but with the exception of a few places where this is a major activity, when you look at industry and you say, okay, how big is your verification team? And you say, okay, we have 100 people. Out of this, how many do formal verification? The answer is it's always below 10%. It's still, with almost no exception, a niche activity. So what is the majority of, how do people really do this verification? Well, most of you, if you've written programs, how did you verify them? You run them on all kinds of test examples to see are they doing the right thing. This, we call it testing, and a fancier name is dynamic verification, which is you simulate the system under different scenarios, and you see, does it do the right thing? And this is, again, this is my own estimate by talking to people in industry, more than 90% of the verification effort. So, especially, I've spent many years consulting with Intel to see how they do it. And they basically, they design the microprocessor, and then they run it under different scenarios. And these scenarios are called input test vectors. Every test vector captures some scenarios, and they kind of know what the result is supposed to be, and they compare it to the actual result to see, okay, is it correct? And what they usually do is, once you build the chip, it's become very expensive, so you do the software simulation of the chip to see does the design do the right thing? And the problem is that the test space is exceedingly large. We cannot really hope to cover all the test space. So let's see one very concrete example. One of the most famous computer bugs was the floating point verification bug that was presented in the Pentium when it was released, I think, 1995. And the bug was basically the chip did not do real division was incorrect in some cases. And Intel had to recall the chip to replace it, and it cost them then about $500 million, and estimated today it may cost over $5 billion to do something like this. And so imagine I want to build today build a divider, a floating point divider with 128 bits. If I want to try all possibilities, the number is 2 to the 56. I mean, this is just, we saw before that 2 to the 200 is bigger than the number of Planck time constants is the Big Bang. So we can never do something like this. So what do people do? So you put an army of people who will think about all kinds of important test cases. You cannot be exhaustive. So it turns out that writing test cases is like writing a code. And the conventional wisdom is that a coder can write about 20 lines per day. So think a coder can write 20 test cases per day. So years ago when I was in IBM Research, they asked me to get involved in the testing of a hard drive controller. They were building, this was big disk drive, they were building a controller, they wanted to test it. So what is the problem? The problem is that we have about 100 test engineers, and everyone writes about 20 test cases per day, so we have 2,000 test cases per day. Now they have bought, instead of running doing the simulation in software, they bought a hardware emulator. This is about 100,000 times faster than software simulation. And all these 2,000 cases, this hardware emulator would run them in a few seconds. And then it would sit idle until the next day, where you get another batch of 2,000. And that emulator cost them, in the early 90s, $5 million. So some manager was feeling really, really stupid for buying this equipment that was being used a few seconds per day. So they came and asked me whether I could help them generate many, many more test cases. And first I said, okay, show me the spec. The spec is a huge volume written in bad English. It was impossible to understand. I said, okay, can I talk to the people who write test cases? No, you cannot. Why not? They're too busy writing test cases. They don't have time to talk to you. So I was not able to help them. Instead, I decided to leave IBM. But someone else at IBM actually came up with a brilliant idea. This was a group, Lichtenstein, Malka, and Aharon, in IBM Haifa in Israel. The idea was, don't write test cases directly. Instead, write constraints that describe a space of possible test cases. For example, you may want to write constraints that says, for this floating point division, both numbers are very large, or both are very small, or one is very large and one is very small. And you write constraints, and then you use a constraint solver. And by now, as we said, we had progress in SAT, so we have very good constraint solver to generate test cases by solving the constraints. But this raised the following interesting question. I have constraints. I don't want just to get a solution to this constraint. I have to get many solutions. I don't want the solution to depend on the internal of the SAT of the constraint solver. What I want to get are random and uniformly chosen at random solutions. Why? Because if I'm looking for a bug, the best way to choose for something, if I know that somebody here is hiding a treasure, what is the best, and I know nothing, what is my best search method? To sample randomly, uniformly. So this gives a very nice, elegant problem. Imagine you're given a SAT formula, and you have a SAT solver, but I don't want a solution. I want to sample solution uniformly at random. How can you do it using a SAT solver? So I asked the people from IBM, how do you do it? They said, oh, we really don't have a method to do that. We put all kind of randomization steps inside the solver. But I said, but does it give you something uniform? They said, no, we don't want to even know how non-uniform it is. But that's the best we can do. So it turned out that this problem of sampling uniformly at random from constraints has many applications. I'll give you one application that I think is very cool. Have you heard here about MOOCs? Open online courses. They've become very, very popular. We can debate them, but nevertheless, they are popular. But if you teach a MOOC, you may have 100,000 students. Now imagine you want to give a homework assignment. You give a homework problem, one student solves it, put the answer on one of the discussion forum, and 99,999 students will just copy the answer. So what you really want to do is create 100,000 different problems. So how can you do it? So one way to do it is you write constraint to describe the problem. You parameterize the problem. You write constraints to describe the connection between the values of the parameters. And then you use random sampling to create independent problems. And therefore, you can generate 100,000 independent problems. So the probability of collision is very small. And it will be very difficult to find collisions. Turned out that this problem of doing constraint sampling is something that theoreticians studied already in the 80s and the 90s. And the ultimate paper by Bellari, Goldach, and Petrank was published in 2000, and they showed that they have a random polynomial time algorithm. So it's a polynomial time algorithm using randomization, random coin tosses, and it calls an NP oracle. What is NP oracle? SAT solver is an NP oracle, for example. And they show how to do it. So in 2011, an undergrad student came and said he wanted to work with me. And I said, how about trying to implement this algorithm? And we implemented the algorithm, and it is scaled. We're only able to scale it to 16 variables. Very small number of variables. Remember, we are talking about that problem with hundreds of thousands, with millions of variables. Now we're dealing with 16 variables. So my students implemented it, and it was up to 16, and he wanted to publish a paper. I said, we cannot publish a paper with 16 variables. He said, why not? I worked really hard on that. I said, when we submit this paper, they will not just reject it, they would laugh at us. Because you have such solver to solve problems with hundreds of thousands of variables, and we're coming up with a solution to 16 variables. So what does industry do? So one approach people use is binary decision diagram. I'll skip it. I want to mention there is another approach. It's called MCMC, which is Monte Carlo Markov chain. And the idea is you construct a Markov chain and you take a random walk on a Markov chain. But in this case, what happens is to get a uniform assignment, you have to take a long time to do this random walk. And most of the time what happens is it takes too long. So people in practice chop the random walk. And because they chop the random walk, they get something which is not quite non-uniform. So this is an important problem. They had really no good solution. And we were able to come a few years ago with the first algorithm that combined two things. It gave you an almost uniform generation. I'll define what is almost uniform. And it did it using randomized polynomial time with the SAT oracle. And this scales to millions of variables. We can really use large formulas. And there are two important ideas here. One is universal hashing, and the other one is SMT solving, and I'll define both terms. So first of all, what is almost uniform? So imagine there is a formula that have kappa solutions. Uniform would mean the probability of each solution is exactly 1 over kappa. That turns out to be very difficult in practice to do, to be precisely uniform. What happens if I said, I'm almost uniform. You give me some parameter epsilon, and I will be within a factor of 1 plus epsilon from this ideal probability of 1 over kappa. So maybe the probability that you want is going to be 1 in a million for each solution, because there are a million solutions, let's say. I will be just within maybe 10% of this uniform probability. So I'll be as close as you want me to be. You give me epsilon, I will be as close as possible to epsilon. Of course, the smaller the epsilon, I'll have to pay the price. The method will scale is 1 over epsilon. So you don't want epsilon to be too small. What is the method? So the method says as follows. Imagine you have, I want to sample someone here. Okay? So one way to do that, I said, okay, let's divide the room some randomly at half. And then I'll choose 1 half. Then I split it in half again. And again, until I get, it's just a small group of people, and then I say, okay, I'm just 1 in 5, I can choose randomly from within that group. So that's what we do here. We divide the solution space into small cell by doing repeated division, random division. And then we choose a cell, which is one of the cells that we got after this repeated division. And then we choose something from that cell. Now, if the cells end up small enough and roughly equal, this will give me an almost uniform sampling. But the challenge is, this is a space I know nothing about. In this room, I see everybody here. But now I have a formula. It has maybe huge number, trillions of solutions. How do I divide them? How do I partition them elegantly in almost equal way? And here comes the idea of universal hashing. So hashing is a very, very fundamental idea in computer science. The idea is I need to map a very large space, 0, 1 to the n for very large n, to 0, 1 to the m for much smaller m. For example, imagine that you need you have a server and you need to store the password. Now the password, maybe can be up to length 100, and using the 2 to the 56 character, the number of possible password is 2 to the 56 to the power 100. It's a very large number. But I want to somehow find a way to store them. And so I want to map them into much smaller space. This is what hashing will do. Now, if the inputs were random, then a good hash function will somehow give you also a uniform output. But we know, for example, that the password that people guess are very far from random. Right? Half of them are 1, 2, 3, 4, 5, 6, and the other half is password. So the beauty of the idea of universal hash function was to say, we're going to define a family of hash function. It's called universal family. And you will choose your hash function randomly from that set. And if you choose randomly for that set, magically it will take an arbitrary input distribution, it will uniformize it. This is a general idea, come from kind of game theory. The way to deal with ignorance is by using stochastic decision. Suppose I have to play a game of rock, scissors, paper, rock, paper, scissors against you, and you may be very good at it. What do? I'll just use a random strategy, and this is the best thing I can do. And in fact, it's pretty good strategy against any other strategy if I just randomize. So that's the same idea here. If I have a uniform family of hash function, it will uniformize the output space. Now, it's not enough to just get uniformity. It's important also to get independence of the different hash values. And why it's important to get independence? So suppose I toss a coin, and I want to tell you if I toss it 100 times, with a very high probability, I'm going to get at least one head. Why? Because I said the probability of tail is 1/2, multiplied by 100. To get all of them tail, the probability is very, very low. But let's assume these are independent coin tosses. So it's very important to get independence of values. And it turned out that to get independence, you have to pay a computational price. The more independent you want to be, the more expensive it is. And so this is an issue. There is a way to get high universality by using higher degree polynomials, but that's expensive computationally. So this is the reason we could not get more than n equals 16 when we implemented the algorithm due to BGP was because they were theoreticians. So they did not care about performance when you implement. They never implemented their tool. They said, let's go for maximal independence. And they did it with high degree polynomials. And this is terrible performance. What we showed is you can go from, instead of high universality, you can go to 3 universality. It means only every 3 output bits have to be independent. But I cannot say that 4 bits are independent. Then that 3 bits are enough to give us almost uniform sampling that enable to scale from tens of variables to millions of variables. How do we do this hashing? What is the magic of the hashing? Okay, this is really this is where the rubber meets the road, so to speak. So the idea is we need to partition the space. We want to partition the space into 2 to the m cells. And we do it by creating linear equalities modulo 2. So each constraint you add here is you take variables and you choose every variable with probability half. You put it in or not, and the sum is going to be, again, 0 or 1. So you get the linear equations modulo 2, and this splits the solution space into 2 by adding this, what we call, you can also think of it as parity constraints. So this is linear equations modulo 2, and I use such equations that gives me 2 to the m cells. And now every cell is defined by a conjunction of the clauses before CNF formula, plus a bunch of linear equations modulo 2 over these Boolean variables. Now, for the CNF, we can use a SAT solver. That would have some very good SAT solver. What about these linear equations modulo 2, or we call them XOR constraints? Suppose I give you only XOR constraints. How do you solve them? High school algebra. Why? You know how to solve linear equations. Just solve them, do everything modulo 2. Just use Gaussian elimination, solve them. So you already know how to solve efficiently XOR clauses. But now we have a combination of both types of clauses. How do we combine these 2 algorithms? SAT solving on one hand, CDCL SAT solving with Gaussian elimination. So one way to do that was to reduce the XOR clauses to CNF. It's possible to do it. Terrible idea. Turn out if you just take linear equations modulo 2, you give them to a SAT solver, and you can do it efficiently, and the SAT solver is terrible because it uses search. It doesn't use algebraic reasoning. It uses search to do that. It's a terrible way to try to solve a linear equation using search. So here comes SMT to our rescue. So what is SMT? SMT is satisfiability modulo theory. After the success, the first few years of success of SAT solver, starting in the mid-90s, people said, oh, can we use it for richer domains of constraints? Can we take Boolean constraints but add linear inequality, bit vectors, what have you? And there was tremendous progress in this field now since 2000. This is a very, very active field. Again, there are very good SMT solvers. We discovered a solver that was developed by Matesus, published a paper in 2009, which was how to combine CNF solving with Gaussian elimination and do it in a smart way. and the solver he developed was called cryptoministat. And this was, for us, it was just, we were trying, and nothing that we worked was successful. And we started doing Google search, and we stumbled on this search. That the interesting about this, that he published the paper in 2009, and the goal was to try to do something cryptographic reasoning where you use lots of bit vectors and parity constraints, and it was not successful. So he kind of put the solver on the web and went to industry. And we discovered the solver, and I mean, he was so delighted that his solver is good for something. So he went back to doing research. So what happened when you put all this together? So one question is, how good is uniformity? So we ran an experiment. We took a problem which is a formula that has 16,000 solutions. And we enumerated all of them, and we built a uniform sampler for this specific problem, and we sampled 4 million samples. And then we used Unigen, uniform generation of samples. And what we got are you get distributions that are statistically indistinguishable. So the almost uniform sampler is statistically indistinguishable from a uniform sampler. What about the performance? So we did a performance of Unigen. We compared it to another sampler called XOR sample prime. And what we got is that we get the performance scales about 3 orders of magnitude better. Okay, so we really you have something here that scales quite well and gives you almost uniform sampling. So the sampling was successful enough that we said, okay, can we use the same algorithmic idea to do something which is more difficult than sampling? And we went to counting. And counting is you're given a formula and you want to know how many solutions does it have. Okay? Now, partly there is a kind of a program here by looking at in some sense, even the sampling. I'm looking at logic probabilistically. And I just want to connect it. I told yesterday in my talk, I said we need to bridge machine learning and logic. And one of the key things to the machine learning is the power of probabilistic methods. And to connect logic and machine learning, it means that we need to start apply probabilistic method for logic. It's not just about is it true or false. We have to start looking at probabilistic information. And in particular, if I want to count how many solutions a formula has, it is related to estimating the probability of this formula being true. Imagine I take a random truth assignment. How likely is the formula to become true? It depends how many solutions does it have. And so this is related to probabilistic inference. But counting solution is known to be difficult. It's defined by Valiant Studygate. It's called SHARP-P. It's a complexity class that's considered to be more difficult than NP, counting solutions. And this has many, many applications, but the key application is Bayesian inference. To do probabilistic inference, again, assuming that I have some probabilistic model and I want to estimate, given some evidence, what is the probability of some conclusion, and you use techniques for model counting to do that. Now, some people, there are exact counters. You give them a formula, they will tell you exactly how many solutions does it have. But I mentioned to you before that we can solve SAT today for industrial formulas with millions of variables. When it comes to counting, we can handle up to about 50,000 variables. So 2 orders of magnitude gap between solving and counting. And so instead of doing precise counting, we can use something before I use almost uniform sampling. Here I will try to approximate counting. And the idea of approximation is called PAC, probably approximately correct. And it was introduced by Stockmeyer in 1983. And the idea was that you tell me your error tolerance, your epsilon, and I will have to approximate the answer within a factor of 1 plus epsilon. But also, I'm going to use a randomized algorithm, and I just need my probability to be bigger than some delta, and you tell me what is your delta. You want 90%? Okay. You want 99%? Okay, you give me the 2 parameters. My method will depend, of course, the closer you are to 1, on one hand, with delta, the more expensive it's going to be, and the smaller the epsilon, the more expensive it's going to be. And there was some theoretical exploration by theoreticians, but again, they develop algorithms that we know today will have no chance of succeeding in practice because they completely ignore these practical considerations. But we went with the same idea of the slicing the solution space, because if I can take my solution space and slice it into small cell, now I can count in a cell. By multiplying it by 2 to the m, the number of cells, I will get an estimate for the number of solutions. And if I sample enough cells, I will get high enough confidence in my estimate. So same idea, take the solution space, slice it into small cells, count the cells, multiply to get an estimate, do it enough time, and now you can take the median, and that will give you a good estimate for the number of solutions. And it turns out that this produced, for formula where you can do exact counting and approximate counting, we found out that even if we use a epsilon of 0.75, that allow us error of 75%, in practice, our error is less than 5%. So the method is incredibly accurate. In fact, it's so accurate that it tells us our analysis is not good enough. It doesn't explain why we are so accurate. We are setting epsilon to be 0.75, and it behaves as if we set it up to be 0.05. And it performs, what happened is that on a small benchmark, the exact counter is better. But the exact counter usually max out at about 50,000 variable. If you want to go to hundreds of thousands of variable, the only way to do it is using this approximate counter. So it's time for me to wrap up, and I want to do it with some kind of philosophical reflection on SAT and on NP. So one is that the goal is, I was trying to tell you that over the past 25 years, the progress in logical reasoning has been dramatic. It is somewhat of a secret. Partly, I think it's a result of bad marketing. They decided to call it CDCL solving, and it sounds esoteric and uninteresting. If they've called it instead deep solving, it would become much more popular. And the point is that SAT solver, just like deep learning is, everybody goes and tries to apply deep learning here and deep learning there, okay? How can I bake a better chocolate cake using deep learning? And SAT solving is an enabler. And I gave you here 2 examples of what we can do with SAT solver, but there are many other applications. There is now an opportunity to go to many problems that so far we have not been able to successfully solve because it requires exhaustive search, and now we have this big hammer, SAT solving. Now, I'm not trying to tell you that scalability is not a challenge, it's an ongoing challenge. In fact, we can generate synthetic problem with a few hundred variables that nobody can solve. But let's go back to P versus NP. When I was a freshman, we had a very charismatic graduate TA, and I remember a few things from that year. So he asked us, do you guys know what is the difference between theory and practice? We kind of come up with all kind of boring answer. He said, no, you don't understand. In theory, they're very different, but in practice, they're very different. And so this is important to understand one hand. P versus NP is a theoretical problem. It's a beautiful theoretical problem. But it's not clear that solving it either way will have much of a practical impact. Why? Suppose that P equal NP, but all of NP is included in polynomial time, which is n to the 1,000. N to the 1,000 is a useless algorithm. It's a useless complexity bound. We can solve nothing of interest. In fact, n to the 100 is useless. In fact, n to the 10 is actually already useless. I mean, just take a very small number, 100, and take 100 to the 10. It's already numbers that are way too large. On the other hand, suppose that P is different than NP. But I can simulate all of NP in n to the log n. So the same graduate asked us, what is the limit of log n when n goes to infinity? So we looked at each other. We said, we're freshmen, but we're not idiots. We know that the answer is infinity. He said, no, you're wrong. The answer is 50. 50, we said, how did you get 50? He said, there's no number in the universe. There's no physical number. If you take 2 logs, you get something which is bigger than 50, right? So because this is 2 to the 2 to the 50. That's a very, very, very large number, bigger than any number in the universe. And so n to the log n algorithm is not polynomial, but it may be incredibly practical. So that means that both positive and negative solution, P versus NP, may not give us any practical implication. We don't know that. And I remember when I was a graduate student, a master's student, I learned about P versus NP. And I thought that NP-complete problems are scary problems, that you can, you have to be careful not to look at them too closely. It's like, what is it? Like Voldemort in Harry Potter, who should not be named kind of thing. But today we solve these huge problems, but there are small instances of SAT that we cannot solve. And so what does it tell us? It tells us that it's not that complexity theory is wrong. Complexity theory is not rich enough. It is not rich enough to distinguish really between problems that are hard in practice and are difficult and are easy in practice. And we need richer theory to make this distinction. But it also means that we should not be scared but just because something is NP-complete. Just because NP-complete doesn't mean you give up. Because we now have effective method to solve them. And BPP to the NP is randomized polynomial algorithm with a SAT oracle. And we need to look for other places we can use such algorithm. And they may end up they're not in polynomial time, but I call them the new P time. And my own view of now what should be P time shouldn't be polynomial time, it should be practical time. Thank you very much. And these two problems